Hi.
Hello, how are you?
Hey, yeah, I'm fine.
Good.
Oh, hi, Wataru.
Hello.
Hi. Hello?
Hi, how are you?
Oh, I'm fine.
Good. That's great.
Yeah, yeah. All right. So it's very late for you, right,
N-
Wataru?
Oh, yeah.
Yeah, yeah. So I will try my best to make it short. Yes,
All right.
not too long. Yeah. So wait a moment. Let me share my screen.
Okay.
So could you see my screen now?
Yeah, it's coming up. There we go. Okay.
Yeah. So right. Our topic today is it is just a temporal name, topology aware temporal graph neural network for cell tracking. Yeah, and it is our research idea, and maybe we will change this name in the future. But the points are topology, graph neural network, and cell tracking. That means we wanna combine topology, data analysis, and the graph neural network to solve some issues regarding cell tracking. And probably you're so familiar with these topics. I mean, such as the cell tracking and GNN. But I want to introduce briefly some backgrounds of automated cell tracking for introduction to our research idea.
Okay.
And first of all, it is about automated cell tracking, which is automated construction of cell trajectories or cell linear tree based on microscopy, images, and videos. And actually, because of huge amounts of data and some weird behaviors of cells, such as occlusion, such as some other behaviors like this, cell tracking of complex species has already surpassed human annotators' abilities. So, existing automated cell tracking works include the classical methods, uh, such as the frame-to-frame methods and uh, such as frame-to-frame methods and globally tracking methods. And the first one, frame-to-frame methods, is to segment and connect cells across successive frames based on their visual similarity or the Euclidean distance. And the globally tracking method is to combine combinatorial algorithms with graph modeling. That means they would model cells as nodes and connections between cells across successive frames as edges. And there are some deep
Are,
learning methods.
are you trying to move
Uh-huh.
your slides?
Oh, sorry.
Are you trying to move your slides, advance them? Because it's still on the first slide, if that's what you're doing.
Uh, I'm sorry, what was that?
Are you trying to advance your slides? Because I only see the first slide.
Oh, you need to see the first slide?
Yeah,
Oh, sorry, wait a moment.
there we go. All right.
Okay. Oh, yes, this is the second slide. Oh, yeah. So could you see my slide right now?
Yeah, I can see the second slide. Yeah.
Okay. Yes. Yeah, in the second slide, I want to introduce the background. Yes. And yes, yeah, uh, I've introduced the existing works at this point, the non-deep learning methods, which is the classical methods. And yes, like what I said, we have frame-to-frame methods and the globally tracking method. This one, globally tracking methods. And also we have some deep learning methods. And there is one type of deep learning methods, which is the frame-to-frame methods. That means people would like to use convolutional neural networks to segment cells and use some recurrent neural networks or some other classical methods to track some series of cell developments respectively. And these are some backgrounds of automated cell tracking. Probably I have limited knowledge of cell tracking, automated cell tracking. So if you have any two compliments, yes, you can just say in our meeting. And next, I want to briefly introduce our motivations of to introduce our motivations of why we combine topology and graph neural network to track cells. And these are our motivations. The first one is regarding why we model cell trajectories as graph, or why use graph neural networks to solve our problems. There is one paper called Graph Neural Network for Cell Tracking in Microscopy Videos, which has been accepted by the EWV 2022, and I will call this paper EWV paper. And this paper has clearly demonstrated the motivations of applying graph neural networks to cell tracking. I will not dive into its details, but I want to introduce some of their motivations. For example, the existing deep learning works only predict frame-to-frame cell associations rather than providing a global tracking solutions like what I introduced before. And the globally tracking solutions have been provided by some classical methods instead of deep learning methods. And as for graph neural networks, it has a better capability to capture graph dependencies via message passing between its nodes. And there's another motivation which has not been demonstrated by this paper, is the topological aspects of a graph. I think that if we only consider the images, I mean the original formats of the data, we can hardly obtain the topological information from those networks. So given these graphs, or given this simply so complex, we have capability to do such things, to view this data from a topological perspective. And the second motivation is that why it's about a question why introducing topological data analysis, such as which is TDA, into our analysis. Because from a lot of works, we know that the topology and geometry are so important for biological network. And existing works regarding graph neural network lack consideration of topological aspects of biological data, especially those cell linear tree or cell trajectories. And in our research idea, I like to introduce the mapper, the topology mapper, into our analysis, but we will homology or a consistent diagram in our analysis. I will explain our reasons. So before diving into our idea, I would like to briefly introduce the idea of mapper. And it is a great tool to extract the political information from a point cloud. Such as this is a point cloud of hand instead of any embryo, but I just want to put this photo to explain the idea of map. For example, given a point cloud point cloud of the hand, the mapper will utilize the function or length function to map this point cloud into a one-dimensional or high-dimensional data, and we will assume that this function will map this point cloud to a one-dimensional data, and or we can say it's one-dimensional embedding, and we will partition this one-dimensional embeddings into multiple intervals, namely covers, and these covers are overlapping, and we will obtain the pre-image. Sorry, could you hear me now?
Yes.
Oh, okay, yeah, and then we will obtain the pre-image of this one-dimensional embedding or one-dimensional covers into this point cloud, and so that we will have multiple overlapping clusters of this point cloud. And as for each cluster, we will regard each cluster as a node. And if there are two overlapping clusters, we will connect an edge between these two clusters. And the benefits of mapper is that using mapper can help us obtain high level representation of a point cloud. Yes, just like if we are
He's out.
Oh yeah. He'll be back in a minute. Here we go.
Hi, could you hear me now?
Yes. Yeah.
Yes. There are some problems with my network. Sorry.
Yeah.
So yes, the benefits of mapper is that we can obtain some topological information, or I can say a high-level representation of a point cloud. Like if we are just directly looking at this point cloud, it would a little bit difficult for us to find that it is actually a hand. But if we look at such a mapper, or okay, we can say such a process point cloud, we'll find that it is very similar to a hand. Yeah, so that is the point of mapper, which is to extract the high-level topological information from a point cloud. But actually, in TDA, people would like to use persistence homology to deal with such a simple complex or other things. But I will not introduce. I will not use persistent homology here, because it seems that you can use persistent homology to extract the topological information from the whole point cloud. But what we focus on at the moment is that each point in this cloud instead of the overall cloud. Yes, I will explain in detail in later. Yeah. So let's introduce.
Sorry. Could you share that slide in that Slack?
Yes. I will share it after this meeting. Okay. Is that okay?
Yeah, that's fine.
Okay. Yeah. So I'd like to introduce our overall structure of our research idea, and so given inputs is a video, is a microscopy video consisting of a lot of images, and the first part is to segment and extract the centroids or the position of cell nucleus from these images. Yes, and this is stage 1 of the level graph. And the stage 2 is to build temporal graphs based on this I mean the data, the output of state 1. So this is an example of temporal graph. We model each frame as a graph, and run temporal connection successive frames, and each connection represents the connection between the mother cell and the cell. For example, these two are daughter cells of this cell, this mother cell, and there will be two connections between them. And then in the third stage of the demo graph, we will apply graph neural network, or we can say topological aware temporal graph neural network to these temporal graphs, and we will obtain a series of embedding such like this. There will be some temporal connections between these embeddings, and our task will be it's just an example. I mean, our task will be predict this temporal connection between successive frames, so we can obtain zero trajectories of these temporal graphs. Yes. Any question? Okay.
Not right now. Yeah, I can hear you. It's kind of a bad connection, but I can hear, like, okay, so step 1 was segmenting the data. Step 2 was build graphs based on output of data. And then step 3 is apply the topological methods to sort of refine the embeddings.
Mm-hmm.
Is that correct?
Yeah.
Okay.
Yes. And stage 4 will be our task, such as the link prediction based on this embedding. Yeah. Actually, there are lots of tasks related to our problems, such as the multi-object tracking, and I'm not sure they will use link prediction to solve their problems. Yes, because link prediction is a common use task in the graph neural network, but probably in other fields, such as the object tracking, they will use some other tasks. So in the future, I would like to dive into other papers to see how they solve such problems. Yeah. So So actually, this topology aware temporal graph neural network, or we can say it's TT-GNN, will be employed on each frame, and each frame will be represented as a graph, and actually we'll find that this pipeline is composed of two parts. The first part is this TT-GNN, which will be employed on each frame, and the second part is how to do message passing between successive frames. And actually, people would like to use recurrent neural networks to pass information from this frame to the next frame. And in the next slide, I would like to describe the details of this TT-GNN instead of the RNN, because by now it's very simple to design such an RNN, because just look at this cell. We assume that we have a TT-GNN on this frame, and with this TT-GNN, we will have a high-level embedding of this cell, and this is the first input of the RNN, and the second input is the hidden embedding of this cell. And given these two inputs, we will have a higher level representation of this node, which is actually the output of RNN. Yes. In short, we can describe an RNN like this, but probably in the future works, maybe we would change the structure of this RNN. Yes. Yeah. So any questions?
Yeah. I can't see the slide, so it's hard to know what you mean by that. But I can see it. Yeah. Why don't we go over this? Yeah. So this is Overall structure. Okay.
Yes.
So this
Yeah,
is
yeah.
yeah. So okay. So framework. So you're going to treat each frame as like an embedding, and then you're going to message
Yeah.
pass between the frames to get these temporal connections, and that's
Yeah.
the
Yeah.
thing you want to solve with an RNN or some other
Yeah.
type of network. Okay. So
Uh-huh.
then each frame is an embedding. So it's like if I have a static image, I get an embedding out of that. And then I
Mm-hmm.
have them for each frame. So if I have 1,000 frames, I have 1,000 embeddings. And they all
Yeah.
represent different points in time. So
Mm-hmm.
some embeddings are going to be similar, some are going to be different. And the way that they're connected is through these message passes, which I assume means that you're passing information about like the change in the graph structure or the embedding structure. So like if say for example a cell divides between one frame and the next frame, then that information would be passed, or how would that work? Or would it just predict things? Would it predict the
Sorry, I'm asking how to propagate information from this frame to this frame.
Yeah. Well, I mean, like
Yeah.
if you have, so you have a change in the network topology, and it looks like you have dotted lines with arrows. So it's passing like identity information. Looks like one cell is going to two different cells in the next frame.
Yeah.
Okay.
Yeah. So actually, I would at the moment I would assume that as for just for example, let's see, look at this cell.
Okay.
Yes.
Yeah.
Because we will assume that the one cell can, I mean, if we think about a correspondence between two successive frames, so we think that this one cell will divide into two cells, but we will not say two cells. Turn into one cell, right?
Right.
So this will happen because there are some weird behaviors of these cells, but at the moment we will not consider it. We will just consider the common things, the common case.
Yeah.
So if we just think about this cell, that means the source of destination from the last frame will be only one cell, right?
Right.
So we can think that there is recurrent neural networks, and there is RNN, and this RNN will take two inputs, and the first input is the GNN on the output of GNN on this frame.
All right.
And we know that each node has its high-level embedding output by the GNN, so that this node will have a high-level embedding by GNN. This is the first input of the RNN, and the second input is we can say the output embedding or the heap embedding or something else of this node. Yeah. So this RNN will take two inputs, which are the high-level embedding of this node and another embedding of this node. They will combine these two embeddings and outputs a higher level of this node. So in this way, this RNN will probably pass the message from this frame into the next frame.
Okay. Yeah.
Yeah.
Yeah, I see what you mean.
Yeah. So actually, RNN is to propagate information between successive frames, and GNN is to propagate information in the single frame. Yeah.
Okay.
Yeah. So any questions? Any more questions regarding this slide?
I'm just taking some notes. Yeah, I have. I don't have any questions. It looks good. I mean, that's the framework. So now, I'll just mention that like some of the images that you'll work with, sometimes it's not perfect information in terms of like cell division and segmenting cells. I mean, you can get it. Well, actually, you can probably get a good sense of how many cells there are. So if you're looking to just build a and embedding, it shouldn't be too bad. But sometimes you do get like errors in segmentation, but with the data sets you're working with, it shouldn't be too bad. So.
Uh-huh. Uh, do you mean I'm sorry, do you mean the embedding? Do you mean this one?
When you're taking images from the microscopy images.
Uh-huh.
So like when you're segmenting the microscopy images, that would be like step one. Sometimes you get errors in the segmentation process. You get like you have to play with the and this is maybe just for step one, you have to play with the different properties of the image so that the images are segmented properly. Because sometimes if the image is not quite right, you get you get saturation or something, and the cells aren't segmented properly. If you're looking for like nuclei of cells, which is probably the best case here, it probably won't be too bad because the nuclei are pretty easily identifiable. And so you'll just have like a map of like these dots, and then you can take that and make an embedding. But just to let you know that, be sure to pay attention to that step one to make sure that the images are like segmented properly and that you don't have a lot of like noise in the noise in the image that then when you segment it and you get the information that you're not identifying cells that aren't there, because that can happen. Yeah.
Okay, I see. But I see that the outputs of Devoren is very good.
Yeah,
right?
yeah, it's usually good. I mean, it's usually pretty good, but sometimes it can be, just because of the way that microscopy data is collected. You get a lot of what they call autofluorescence, which is noise in images. In some images, that's not so bad. In other images, it can be worse. So that might carry over. So yeah, I would just maybe have like a step, like a step 1.5, where you like kind of look at the images and then make sure that the segmentations make sense. Like, that there are no obvious like errors in the segmentation.
Yeah. I get your point. Yes. Yeah. Actually, this you remember this one? Sorry.
Yeah.
This paper, the EWV paper, and actually this paper has done some works like segmenting those images and to obtain their positions of their cell nuclei. And I think maybe we can refer to how they implement such a step.
Yeah.
Yeah.
There's an automated way to check probably because it's really because, what DevoLearn is doing is basically taking an image, taking out like markers that you define, and then it's like giving you some numbers or some other sort of image that just gives you just those points. But if there are points that it misidentifies, then you have a problem. So you have to make sure it's you have a checking step to make sure that you don't have any glaring errors. Otherwise, your different frames are going to be inconsistent. You won't be able to, you're going to message past something that isn't there. And if you put the annotations on it or something later, it's not going to make any sense. So, but I mean, that's something that we've just had problems with in years past where, we don't want to, especially when you do like a large batch of data, you sometimes get a little bit of an issue with some of the images.
Okay.
And then I like this. I like the structure of this where you're message passing to different frames. In years past, we've tried to work with like the temporal aspect, and we've kind of not done we've kind of focused on the different frames as discrete things. So like, that temporal flow is the thing it's really kind of tricky to get right. So that's like, message passing is a good, I don't know, you haven't implemented it yet, so we'll see how well it works. But I think I understand what you're doing. You're just basically taking information from one frame, applying it to another frame. You're passing a message about what was and then what's in the next frame, and then you keep doing that across the different frames and that gives you, yeah.
Yeah. Actually, in that paper, in WCV paper, what they do is actually they did not model those images like this graph. They just model the whole cell trajectories as one directed graph, and they would connect nodes between successive frames if the nodes have mother and daughter relationship. For example, in this graph, in such an example, though that's the paper, the EWCV paper will not connect nodes, between. Will not put the edges in the frames, such edges, these edges. They will only connect nodes between two frames with such a temporal connections, and this temporal connection in their work is the directed edges in a directed graph neural network, and they would just propagate information like what graph neural network would do, and yes, that's what they do. And actually, how they connect nodes between successive frames is they would check the Euclidean positions between those nodes. For example, if in this frame, these two nodes are very close to the node in this frame, or we can say we can put these nodes and we just drag this node in this frame, and then we will check their Euclidean distance between these three nodes. And if they are very close, they will connect edges between these nodes. Yes, it's like what KNN would do, KNN graph, K nearest neighborhood graph would do. Yeah.
Well, yeah, that's good. Just so if like you have a cell that divides, and it results in two cells, those cells, if they're near one another, get connected. What if they divide and go to the other opposite ends of opposite sides of the embryo? What then? Because that's what happens in C. elegans. You get like a division and one goes left and one goes right. I don't know what the distance is between them all, but like, I guess if they're unassigned, then it could connect. You might have to play around with that a little bit, just to know.
I'm sorry. Do you mean once there goes out the frame, goes out this image?
Well, no, it's just that like when a cell divides, as I understand it, in the next frame, it'll connect it if it's close enough, or if like a K nearest neighbor will just connect things that are close.
Mm-hmm.
But what if the cells in the time that you have these two frames, they migrate far away from one another in the frame, so they're in different parts of the frame instead of in that at the top. Say there's one at the top, one at the bottom, and it's part of that same lineage. I don't know how often that would happen, but it might happen. We don't know.
Yeah, I think it is a question. Yes, because actually, it is related to how we model such a graph in a single frame, right? If we use KNN to model such a graph, maybe we would not collect that. But actually, my point is that I think, look at this image. These two nodes, right? And these two nodes comes from the same mother cell, but this image doesn't mean that these two nodes come from the same mother node.
Yeah.
You know what I mean?
Yeah.
Yes. So I think this edge is in the same frame just help us to propagate information, propagate message in a single frame, in a single graph. It doesn't mean that when this each connect two nodes, then two nodes come from the same mother cell. It doesn't mean that, right?
Right.
Yeah.
Well, yeah,
So,
that's true. Yeah,
yeah.
it doesn't have to be. So yeah, I guess that makes sense. You could just connect it like using a KNN type method, and then just annotate the embeddings later and say these are related. These are daughter cells. These aren't daughter cells. And we can talk about we can make inferences from the embeddings later. I guess it's just a matter of getting a quick embedding based on nearest neighbor criterion, because we can use other criterion, we can use any criterion we want actually to generate embeddings. It's just a matter of what do you want, as long as it's consistent across frames. That's all that really matters. So yeah, that works.
Yeah. Actually, because we are considering, when we build such a graph in a single frame, we are considering its distance, but but it can be some other distance instead of the Euclidean distance. If we are regarding such a frame as a manifold or some other geometry, maybe we will use some other kind of distance. But yes. Yeah. But actually, I think it is not our most important points here. Yes, because our point is, how to model such a graph in a single frame. Yes, we can discuss it, but it's not our most important point. Our point is that we connect such a graph, we build such a graph for each frame, because we want to propagate information in each frame. And more important, I will explain in the next slide. More important is that this message passing in the single frame will help us to perceive the topological information of this frame, of this network in a single frame. Yeah. Yes. So it's like if you model this graph based on other geometry, based on other kind of distance, such as some manifold, hyperbolic manifold, you will build a different kind of network for this frame. And when you are propagating information in this frame, you will obtain some other kinds of topological information for other kinds of geometry, such as the manifold. Yes, actually there are lots of choices, but the most important is that we build such a graph for such a frame, is that we wanna use the topological information of this frame, of this point, this term. Yes, and we think, I'll explain in detail in the next slide. Yeah.
All right. Yeah.
Okay. Yes, and actually, I think you asked me these questions. I think maybe I didn't explain clearly our motivation. There's one point I didn't explain, is that just look at this slide. Is that actually we all know that graph neural network on a point cloud can help us to propagate message. That means each node in each point in that point cloud can obtain the information of its locality, that is its neighborhood. But why we use mapper is that we know that a shadow or a GNN with small number of layers is always the best structure of this kind of GNN, such as a 2 or 3 layer GNN is better than a 5 or 6 layer GNN, and some research works has showed that. And if the number of layers of this GNN is very small, then as for each point in that point cloud, you would only perceive information of this small locality, this small a range or this small neighborhood. Yes, but this small neighborhood, the information of this small neighborhood will not help the node in this range to perceive the topological information of this locality. Yes, and I think the more important is that if a node, a point in here can perceive the topological information in this range. Yes, yeah. like you can perceive the position or some kind of means of positions in this point cloud or in this topology. Maybe it will help you to I don't know how to explain it clearly. Maybe it will help you to track cells. I mean to think of it as embryo, as some kind of embryos, and embryo will say the cells here, the cells in a certain position of this topology will develop into some certain positions. Like in the next frame, they will move to here, move to here, move to here. I mean, if a certain cell can perceive a larger range of its topology, it will help it to to build cell trajectories. I don't know if I explain it clearly, and I'm not sure that's yes.
Yeah, I think so. And it's like in development, you do have actual development. You do have something called positional information, which is where the cell is responding to its location in relation to other cells or where it is in the embryo. And that might be the same principle here, where you have, locally it knows what's going on locally, but not necessarily globally. And that's but you piece it together, you can get something like this hand. You have this point cloud of different points. The points maybe respond, or they have they describe their neighbors maybe, but then if you go to the global scale, you need to have all the cells are kind of doing their own thing, and then you end up with this hand or this structure here on the right. I mean, I'm just, I understand kind of what you're saying about like the process of analyzing this. So I'm not familiar with Mapper. Is this a technique that people use for TDA?
Yeah. Sorry.
Oh,
was that?
Yeah. Okay, yeah. Is Mapper a common technique for TDA? I'm not familiar with it so much.
Okay, yes, and yes, just like what you said, the point is that if we can, it's also like a cost grading. Yes, you obtain some high level representation of this point cloud. Yes, I mean, if you can think that if we use Mapper to the point cloud as this kind of network. Then, as for, and we can think that we have points here, and after this mapper, and we will have points in here, and actually these points will be located in here, and it's like cluster. And then when you're doing a message passing on this network, that means the points in this cluster, and you can see my cursor. You can see where I'm going to. Oh, could you hear listen to me?
Hello?
Oh, could you listen to me? Can you hear me?
Yeah, it's breaking up a little bit. You could shut your camera off, maybe. Sometimes that helps.
Oh, could you see my screen share now?
Yeah, I can see it. Screen share.
Yeah, so could you okay. Yeah. So I mean, my point is that let's look at the points here, and we can think of a mapper as some kind of cluster or some kind of coarse graining. and the mapper has clustered nodes, the points here, into a single node here, right?
Yeah.
And if we do message passing on this network, that means this node will perceive information of this locality, this small locality, right? That means this kind of, this mapper will help this node to perceive the topological, some information. Maybe it's not topological, but some information in this locality, right?
Yeah.
Yep, but because we know that sometimes the graph neural network model have to be shallow, they can only have small number of layers, such as 2 or 3 layers. Yeah, I'm not sure. I'm not sure how much I have introduced, but the point is that because we know that the graph neural network model is always shallow, that means they can only have small number of layers, such as 2 or 3 layers. So if we employ a graph neural network on such a points cloud, then the points here can only perceive the information of its neighborhood in a small range, such this range, right?
Yeah.
Then such a node can hardly perceive the topological information of this locality, because in this range, a point doesn't know the position of it or the topological information of it, right? We are more considering, as for this node, we're more considering such range of topological information, right?
Yeah.
So such as we would like to know which finger the points is located in. So if we can perceive the information of this range, these 3 fingers, then we will know this points located in this finger, the smallest finger. But if we can model a point cloud as this network, and we just use a shadow graph neural network model on this network, then by the message passing, this node will perceive information of this locality. Then it will help us to perceive the topological information of this locality, right?
Yeah.
Yes, I'm not sure if I explained clearly.
Oh, I understand. I understand.
Oh, okay. Yeah, that's great. Yeah. So that is why I didn't use persistent homology or persistent diagram here, because in my understanding, I think persistent homology will help us to, help the model to know how many circles, how many voids, or the overall structure of the whole points cloud. And it will help model to obtain a high-level representation of this whole graph instead of a small locality. But in other words, if we are only considering a subgraph, such as small range, and we use persistent homology, persistent diagram on this subgraph, then we can only obtain a high-level representation, topological representation of the subgraph. It is also okay, but we can try it in the future. But if we only think of just like what topological graph neural network has done, I remember that the paper that work is focusing on the graph classification, and node classification is not as focused. So with the persistent homology or persistent diagram, we can have the topological of this whole point cloud instead of small locality. But here, what we focusing on is the small locality or a certain point. Yeah, so that's why I didn't consider the persistent homology here. Yes, but just like what I said, if we only consider the graph or the sub-point cloud of this point cloud, and we use the persistent diagram on this subgraph, then we can obtain the high-level topological representation of this graph. Then it would also help the model to perceive the information, topological information of this locality as for a certain node, a certain point. So it would also work. We can.
Hi.
Sorry. Yeah. Yeah. I lost my connection again. Sorry. That's so bad. Yeah. Wait a moment. Let me. Okay.
There we go.
So, could you see my screen share now?
Yes.
Yeah.
Yeah. So, let's make it short because I think it is very late for Wataru.
Yeah.
Yeah. Yeah. So, this is the last slide, which is the TT GNN, and the TT GNN will be employed on each frame. I mean the graph of each frame. Like what I said, these temporal connections will be operated by the recurrent neural network. So as for the graph of each single frame, we will consider the TT-GNN, which is the topological aware temporal graph neural network. And this is a graph neural network which combine ordinary graph neural network and topological mapper. And the first part is the GNN, which is just simply propagates information on this graph to obtain ordinary embedding of this graph, which is this one. And if you could not hear me clearly or something else, just type in Slack so I will know. Yeah.
Oh, this is very good. Yeah, the quality's
okay.
a lot better.
Yeah. Okay, that's good. Yeah, and as for this graph, we know we would extract the 3D position of cell nuclei or centroids or something else, and we would call these positions as topological information, or we can say ordinary topological information, such as three-dimensional coordinates as this matrix, and we have such length function. This function will map the positions matrix into a one-dimensional embedding. And this length function, I remember this one paper called Deep Graph Mapper, and I have notes introduced here, and I will share this paper in Slack. And this Deep Graph Mapper, this paper also motivates our design of this TT-GNN. And in that paper, they use graph neural network here to map the embedding, such an embedding into the one-dimensional embedding, such a matrix into one-dimensional embedding. And we think the graph neural network can help us. It will be a very small graph neural network because the dimension of input matrix is small. It's only 3 or 2. So this graph neural network will be very small. And this graph neural network will help us to obtain some topology, some positional information of this graph. So to show the topological information from a certain perspective, and we'll have such a one-dimensional embedding, and we extract the overlapping intervals, such as this color word embedding, and we obtain its pre-image, and we will do some pooling, some simple pooling, such as to obtain the mean value of each interval or each cluster, then we have a pool graph. Yes, and it is very similar to that hand point cloud in the previous slides. Yes, and you might remember that we have some point cloud, and we use mapper to obtain a high-level network, and it is very similar to the process here. We have a original point cloud or original network, and we use mapper to obtain a pooled graph like this. And actually, in practical case, this graph will have a lot of points, a lot of nodes, and this graph will have a small number of nodes. And then we will use another graph neural network, or I would recommend using graph neural network here, but we may have some other choices to make each cell here to leverage its high-level topological position or topological information in their certain frame. That means a node here will perceive the topological information of its locality. Then, after this graph neural network, this small, very small graph neural network, because this graph is small and probably its dimension of its feature is also small, so this graph neural network will be small, and we will have another embedding. And we'll find that this embedding is actually for the node here, the nodes in this graph instead of this graph, instead of the original graph. So we will combination the embedding here and this embedding. We combine these two embedding to form the output embedding. Yes, maybe it is concatenation, or maybe it just sum two embedding. Yes, we can try. We can do some experiment to show which is better, and after that we will have an output embedding, and we find that in this output embedding we have the information of original point clouds, original network, and we also have the information of the network after the mapper, after the mapper processing, and the information of this network will help the nodes in the original network to receive the topological information in its locality, in a larger range of locality. Yeah, so this is the design of TTGN. Yes, I'm not sure if I explained clearly. So, any question?
Yeah, I mean that's good. I think I don't have any real questions right now. Thanks for presenting on that. And I think it's once you get like some examples running, maybe you can do a small scale run through with like the actual data just to show that it works, and then scale it up. Like when you start to get your different stages accomplished, and then you put it into this. I wouldn't like do the whole thing at once. I'd start very small, and then show how that works from step by step, and then you can scale up and validate it. And I mean, the validation I don't think is going to be. I mean, you're probably just going to use the data that you have, but I don't know. Well, that it might not be a bad idea to actually have like a validation step where you're kind of making sure that it's working. It's matching what you expect in terms of the output.
Yeah. Actually, because we're not pretty sure this structure will work, but we will need some outputs of GSoC projects. So, basically, if this structure doesn't work for GSoC projects, because you will find that our design of this structure is aligned with what we design for GSoC, what we design for Devil Graph. But if the output of this structure is not very well, maybe we will consider using the structure from this EWV paper.
Okay.
Yes.
Yeah.
Yes. Because it's because there's few words regarding how to employ graph neural networks on this developmental analysis, and we cannot sure. It's not like the convolutional neural networks. We have such as the ResNets. We have a lot of pre-trained network, and a lot of large data sets, such as the ImageNet, has guaranteed that this convolutional network can work on a lot of large data sets. But actually, as for the graph neural network, we have no such a such a classic network structure which can really work on various types of data sets. So what we can do is just to try this network. Yeah.
Right.
Yeah. So yes. So, and actually, as for the structure, there are still we've implemented some drafts of the step 1 and step 2, and I'm still implementing the step 3.
Okay.
And now probably because we want to try some real data set. That means we will try to modify the stage 1 and stage 2. Yes, so we will go back to these implemented stages. And as for these 2 stages, I will need Wataru to do some difficult works, I think.
Okay, yeah.
Yeah.
So Wataru's job is the 1 and 2, as you said in Slack, I think.
Yeah. But actually, I've contacted the authors of this paper, of EWCV paper, and they have done some graph neural network on these videos. And I think, I remember they said they will release a new version of this paper and their source codes in GitHub in this week or maybe the next week. And I think that's if they release their source codes, it will help you to build the pipeline of the step 1, I think. Yes. Yeah. What do you think? Yeah.
Yeah, he said yes.
Okay. Yeah.
Okay. So I guess I just want to make sure that you're dividing the work up, and it looks like you are. Now, like for GSoC, you have to submit some work, and of course you're kind of working together, so it's kind of hard to just make sure that you sort of have your own sort of work defined so you can write it up. Because when you do your final evaluation, this is going to be later in the summer or in the fall, you're going to have to write up what you did and submit something to GSoC. So I don't know how we'll divide that up, but we'll figure that out, how to divide up the parts for that, just to make you aware of that. The other thing is that I hope that as you're working, you take notes. And we have different methods for taking notes. You're welcome to use your own method, but we usually use different tools, like something called Obsidian, which is a nice tool for like taking notes and organizing them. We also use other types of like README files and things like that, which you can also use to just make sure that you're keeping track of everything. And it looks like you've got slides. At least Jiahang has slides that he's like kind of going through and putting things together in. So but I just want to make sure that we have that, so that when we go back at the end of the project, or we go back like next year or something, we can go back and look and see what was done. Because this is very complicated work, and we should have like notes on what was done, what steps are taken, and then if you're using like different parameter values for things, if we have those recorded somewhere. And I just want to make sure that happens. I want to make sure I say that in advance so that we can have that happen. Yeah.
Okay. Yes.
Yeah.
Speaking of the dividing our work,
Yeah.
I'm thinking of try some GNN transformers.
Okay.
Actually, I'm interested in transformers, so I'm searching for some works of GNN transformers. Yeah.
Right.
Actually, I found some of them applied to like pedestrians or some other tasks. So yeah, I'll try to find some. Yeah.
Okay. Yeah, but I think this is good that you're like dividing up the parts, so you have like an infrastructure to go forward on. So, I don't know what the GNN part will look like. I mean, we have some good candidates, and we'll see what works well. But yeah, that's the other thing too. Is like we have these different candidate approaches. We can try different things and compare them. I think because it's so open, we don't really know what'll work well. Having a couple of different things that are working will help us understand like which ones are better, which ones are worse. So I mean, I don't want to put too much pressure on you to like go implement everything, but just make sure that maybe we could have like two different approaches as rivaling approaches, and then see which ones are better, which ones don't, because we don't really know if this looks like it'll work, but sometimes it doesn't. Sometimes it's easier said than done. So just to keep that in mind.
Yeah. Okay. Yeah. I think we will try. Yes. Oh yeah. Yeah. Oh, actually, as for Wataru, you said the graph transformer. Yes. Actually, because I've just assumed that to put some GNN on each single frame, it can be any kind of ordinary GNN, such as GCN, GAT, graph sage, and yes, it could be the graph transformer. Yes, and I think I'm not sure. Did you say the graph transformer network, that paper, GTN?
Yes.
Okay. Yes, I remember that paper. But I remember that was designed for heterogeneous graph, right?
Yeah.
Okay. Yeah, I will check that. Yeah, because my bachelor dissertation is about heterogeneous network, so I've checked this paper before. Yeah.
Sorry, I'm still a beginner in GNN, so yeah, I don't understand the types of GNNs.
So, that's okay. Yeah,
try to study.
Mm-hmm. Yeah. Okay, graph transformer. Oh yeah, and actually, I think you can, if you are interested in graph transformer. I mean, in practice, if we want to do something on this structure, we have to compare different GNN structure in our model, because we do not decide which structure is better, which structure is best for our structure. So we need to compare them. So graph transformer is a good choice. But actually, I remember GTN is designed for heterogeneous graph instead of our graph, because it seems that our graph will be homogeneous graph. And I think you can search another work. I don't remember its name. You can search transformer for graph, transformer on graph, or something else, and it has a similar name, but it is actually totally different from the GTN. Yes, and in last year, there is a competition in the Open Graph benchmark, and this organization has held a competition, and I remember the first rank is not any kind of graph neural network. And I mean, this competition is to compare which which graph neural network is the best is the best on some large scale graph data sets. And remember, the top rank is not any kind of graph neural network. Actually, it is transformer. Yes, it's very weird because the transformer, since that the transformer does not take any type of message passing, or it is not accurate to say that. I mean, it is not similar to any kind of existing graph neural network. And I think you can try to search the transformer on graph instead of the graph transformer, because the graph transformer, or we can say GTN, is specifically, it's actually designed for heterogeneous graph. But the transformer on graph is better, is more powerful, and it can two ways more types of graphs. And I think if we want to try some transformers, that transformer on graph is I think is suited for us. Yeah.
Okay. Thank you for the information.
Yeah. That's okay. Yeah.
Okay.
Yeah. So yes. Oh, by the way, Bradley. So you just mean that we need to make some notes and some logs, right, to log our procedure, right?
Yes.
Okay, so understand your points. Yeah.
And it could be in the form of a digital notebook too. We've often done that in GSoC projects. So it could be like a collab notebook, and you can save text in there as well as code. So that's actually like where you can put everything in an order, and then it kind of has a logical flow to it. So you can see the steps and link the code to it and all that.
Okay. I understand. Yeah. Yes. Okay. And actually, I think because this idea, although we cannot sure that it will work, but it seems that this work is aligned with the GSoC project's design. So I mean, if it really work, besides submitting some outputs to GSoC, we can also submit some papers to some journals and conferences.
Oh yeah.
I think.
Yeah, definitely.
Yeah, basic work. Yeah. So yeah, it is just actually this idea is just a draft. We still need a lot of things to try, a lot of things to modify. Yes, and I think from this week or the next week we will try to write some codes and do some experiments. Yes, I think. Yeah.
Okay, yeah, that's very good. Yeah, definitely. And don't just like kind of go all over. Just kind of like maybe if you do an experiment, do a very simple comparison. Like, you might try two different models, or you might try the same model with two or three different setting, parameter values or configurations, just to show like what maybe works better, or just, kind of think about like what's the best set of things I can put head to head and see if they work. And then you can test them out that way, because if you otherwise you're just going to get bogged down in thinking about like every little thing, and but the best way to do it is just to have like a couple candidates that you're going to go ahead and test out and see which ones are better, which ones are easier to implement, and then we can evaluate it when you get the results. And
yeah, okay, I understand. Yeah, so yeah, that's cool. So I'm done today. I have nothing more to show. So do you have any question or not?
I'm okay. Yeah.
I'm okay.
Yeah, okay. So we done today?
Yeah. All right. Yeah. Thanks for the update. That was very informative.
Okay. Yeah, thanks for listening.
Yeah. Good luck to you too, and hopefully, if you have any questions, send a message in Slack, and I'll always respond to it. So.
Okay.
Yeah, thank you.
Yeah.
All right. Thanks.
Yeah. Thanks. Yeah. Thank you. Yeah.
Talk to you later.
Bye, Brady.
Bye. Bye.
Bye. Bye.